Hello everyone, welcome to the series of lectures on the course Calculus and Numerical Methods. This is the continuation of the previous video that I posted on Newton-Raphson method. In this lecture, I will talk about some applications of the Newton-Raphson method. So let's recall what is Newton-Raphson method. So given any function, I can find the approximate root of that function correct up to the desired accuracy level using this method known as Newton-Raphson method, right? And we saw problems also based on this method in the last video of numerical methods. So what we do here, given any approximate initial root x0 of this function f, the n plus 1th approximate root of this function is given by the iterative formula xn plus 1 equal to xn minus f of xn upon f dash of xn, and this is valid for each n in A. Okay, so this is called the iterative formula for finding the n plus 1th approximate root. Now let's see some applications of this. So consider this one. Find an iterative formula to find square root of any given positive real number. So if I give you any positive number n, capital N, real number, then how can I find an iterative formula to find the approximate value of the square root of that real number? For example, if I give you 3, I need an iterative formula that will give me the approximate value of root 3. Alright. So I want to do that in general. So I have picked up a positive real number capital N, and I need an iterative formula to find square root of n. And hence using this, we will find square root of 5 by putting capital N equal to 5. Alright. So what we have to do, we have to find the square root of n, right? So square root of n will be some real number, let's call it x. Okay, so let x be equal to square root of n. So I have to find the value of x now, which is equal to root n. Sorry, this is capital N. So root of capital N, right? So if I square on both the sides now, what I'll get, x square is equal to capital N. So I have to find a real number x such that x is equal to root of capital N. That is same as finding a real number x whose square is capital N, because both these statements are equivalent to each other, right? Both these equations are same. And this is same as saying x square minus capital N is 0. So I have to find a real number x now such that x square minus this n capital N which is given to me, that will be equal to 0. Fine. So what we do, we take this function as f of x. Okay, so consider the function f of x is equal to x square minus capital N. So I have to find a real number x such that x square minus n is 0. That is, I have to find a real number x now such that f of x is 0, because I have defined f of x to be equal to x square minus n. And that is as good as finding the root of this function f of x, right? I need a value x such that x square minus capital N is 0, and that x will be nothing but the root of this function f of x, which we have defined to be x square minus capital N, right? So our aim now has reduced to find this approximate root of this function f of x. Okay, so now we have to find approximate root of f of x. Okay, so now the Newton-Raphson method will come to a help, and using that we will find a iterative formula to give the square root of any given positive real number. All right. So supposing I have the initial approximate root that is given to me. So let's consider that to be x naught. Let x naught be the initial approximate root of f of x. Approximate root of the function f of x. Then by Newton-Raphson method, then by the Newton-Raphson, or in short NR method, how can we compute the n plus 1th approximate root? We have already done this. The n plus 1th approximate root is given by the expression. I will write it down here. Sorry, I have used x, so let me stick to x. So xn plus 1 will be equal to xn minus f of xn upon f dash of xn. This is what we learned in Newton-Raphson method, f dash of xn. Right? So f dash of xn is the derivative of the function at the point xn. So the function f that is given to us is f is equal to x square minus n. So if I differentiate that, so here f of x is x square minus capital N. So if I differentiate that, f dash of x will be equal to 2x, right? And because capital N is a constant, that its derivative will be 0. So f dash is nothing but 2x, right? So if I substitute this data here now in the function, in this expression, let me call it star. So substitute this in star. What do we have? Xn plus 1 is equal to xn minus f of x is x square minus capital N. So what will be f of xn? You just replace x by xn in the expression for f of x, right? So that is going to be xn square minus capital N upon f dash at xn. F dash at x is 2x, so f dash at xn will be 2xn, right? You just replace this x by the term xn. So if we simplify this, you will see that this is nothing but, I can just cross multiply this 2xn there. So that will give me 2xn square, right? And I can open up this negative sign inside the bracket. So that will give me minus xn, minus into minus, plus capital N upon 2xn, right? A simple simplification there. And 2xn square minus xn is xn, sorry, this is xn square here, yes. So 2xn square minus xn square is 1xn square, so I'll be left with xn square minus plus capital N upon 2xn, right? So if you want, you can leave it at this stage, or if you wish to keep that half outside, you can do that as well. Okay, and then distribute xn, so that will be xn plus capital N by x. So you can keep this half 1 by 2 outside, and then distribute this xn to xn square and n. When you give it to xn square, 1 xn will go from the numerator, and I'll be left with 1 xn, and you divide capital N by xn, and that will remain as it is. Okay, so if I want to find approximate square root of any positive real number capital N, then what I have to start with? I have to start with the initial approximate square root of that. That will be x naught. Then using x naught, I can find x1 using this expression. So xn plus 1, we can see that is equal to half xn plus capital N by xn. So if I want to find x1, what will be x1 from here? It will be half x naught plus capital N by x naught. So using that I can find x1. Same way I can find x2, x3, and by proceeding in such way, I can actually find the approximate square root of the given real number, positive real number, capital. Okay, up to the desired accuracy level that I need, whatever accuracy level, it depends on you now what you need. So depending on that, I can find the approximate square root of this capital A. Okay, so this is the iterative formula that I was talking about, and that's very important to find the approximate square root of capital A. Okay, then the question says, hence find approximate root of 5. That's capital N equal to 5. Okay, so to find root 5, you just have to replace capital N by 5 there. Okay, so what will be the iterative formula? Xn plus 1 will be equal to half xn plus capital N is 5, so 5 by xn. Right? Now, if you look at root 5, okay, if you look at 5 now, uh, the perfect square before that would be 4, so that will be root 4, and just after this would be 9, right? So that's root 9, and this is 2 and this is 3. So this gives me a hint somewhere that root 5 must be lying between 2 and 3. So I can pick up 2 as my initial approximate root, right? So I will choose x naught to be equal to 2. That is the initial approximation. Okay, because I can find a perfect square before and after 5. That's 4 and 9, and root 4 is 2 and root 9 is 3. So root 5 must be definitely between 2 and 3. Okay, so using this formula now I can, x naught is given to me, so I can find x1. So what will be x1? That will be half x naught, the previous term, plus 5 by, sorry, x naught is how much? Yeah, let me write it down once. X naught, but x naught is 2, so that will be half times 2 plus 5 by 2, right? And if you simplify this, this will turn out to be 4 plus 5, that's 9, 9 by 2, and this will be 9 by 4, right? And if you try to write this in decimal form, you will see that this turns out to be 4 to the 8, so 2.25. So that's the first approximate root, that's 2.25. Okay, so let's compute few more. I need to compute 4 as per the question. So let's compute x2. x2 is from the iterative formula, so this can be written as half x1 plus 5 by x1, right? But x1 we have just computed that and it turned out to be 2.25, so this will be half 2.25 plus 5 by 2.25, right? And if you put this in your calculator, you will see that this turns out to be 2.23611. Okay, you can just verify this answer on our calculators, and that will be x2. So in a similar way, I can compute x3. I need 4 iterations. So x3 is half x2 plus 5 by x2. x2 we have already got now, so this will be half into x2, that is 2.23611 plus 5 by that same number, 2.23611, right? I can just rewrite this. 2.23611. All right. So you can put this in your calculators again, and you can see that x3 will turn out to be 2.2360. Okay, so slowly we are moving towards the exact square root of 5. So last one, and the fourth approximation will be half x3 plus 5 by x3. x3 we already have now, so I can just drop that value here. So that will be half x3 is 2.2360 plus 5 by that same value 2.2360. Okay, and if you put this in your calculators, you will see that this number turns out to be 2.236067,977, and that is the fourth approximate square root of capital A. That is 5 in our case. So square root of 5. Therefore, square root of 5 is equal to 2.236067977. Approximate value, yes, approximately equal to, and this is up to the fourth iteration. Alright, so if you put in the calculators, you will see that the value of root 5 is very close to this value. So that's how, given any positive real number, you can find the square root of that using this formula. It comes from the Newton-Raphson method, and the iterative formula I have already derived. Yeah, that's here. Okay, so that's the important one. You can mark this as an important one, and you can use this iterative formula to find square root of any positive real number you like. Okay, so what you all can do is you all can try, I'll leave this as an homework, find square root of 3 and let's say square root of 7, correct up to 4 iterations. Okay, so you can find the first 4 iterations. Alright, so you can experiment the above method on these two numbers, root 3 and root 7, and try to find approximate values for them. Alright, next I can expand the same method. We did it for square roots, so you can expand it for cube roots, fourth roots, fifth roots, any higher order root you like. Okay, so find an iterative formula, to find n raised to the fourth root of n. Okay, and that is nothing but, or you can say n raised to 1 by 4. Okay, another way of writing the fourth root of n, you can write it this way also, any way you like. So of course n is positive here, then only I can talk about their roots. Okay, so n is positive. Okay, so here also we will find for the first 4 iterations, and that will be the approximate fourth root of this n. Okay, so supposing it is equal to x, that's the fourth root of n. Then taking fourth powers on both the sides, power 4, this will be x raised to 4, and this will be, you can in fact write the other expression here if you are not comfortable with this one. I can write n raised to 1 by 4 also, same thing it is. Okay, just another way of expressing. So when I take power 4 on both sides, this will be n raised to 1 by 4 the whole raised to 4. And by laws of indices, the powers will be multiplied, and hence this will be equal to n. Right? So I need to find a real number x such that x raised to 4 is equal to n. and that is same as finding a real number x such that x raised to 4 minus n equal to 0, right? So I will consider that function now to be f, right? And now I can find its derivative as well. That's f dash of x would be 4x cube, and derivative of n would be 0, right? So by Newton-Raphson method, what we have is, if x naught is the first initial approximation, then xn plus 1 is given by xn minus f of xn by f dash of xn, right? Where x naught is the initial root. So if that is xn plus 1, then what will be xn? F of x is this. So f of xn will be xn raised to 4 minus capital N upon f dash of xn will be 4xn cube, right? And if you simplify this, cross multiply, that will be 4xn raised to 4. I can open up this bracket, the negative sign inside the bracket, so that will be minus xn raised to 4 plus xn by 4xn cube, right? And if you simplify this further, that will be 3xn raised to 4 plus capital N upon 4xn cube, right? And if you still further want to simplify this, you can leave that 1 by 4 outside and distribute the denominator xn cube to both, so that will be 3xn plus 4 by xn cube. So that is the approximate n plus 1th approximate root for finding the fourth root of capital N. Alright, so that will be 1 by 4, 3xn plus 4 by xn cube. As an exercise, I will leave this for you all. Find fourth root of 5. Okay, compute 4 iterations. So iterative formula is already there now, and you just have to look out for the initial approximate value, initial approximation, and compute the first 4 iterations to get the approximate value of fourth root of 5. Okay. Next, we will see how to find the reciprocal of any given non-zero real number. Okay. So let's start with a non-zero real number. Let n be a real number, capital N, which is non-zero. Alright, so I have to find 1 upon n using Newton-Raphson method. Actually, I have to find the iterative formula for this. Find the iterative formula for 1 by n using Newton-Raphson. So I need to find 1 by n. Supposing x is my 1 by n, right? So I can just cross multiply and I can rewrite this as n equal to 1 by x, and I can rewrite this as 1 by x minus n equal to 0. So finding x such that x equal to 1 by n is same as finding x such that 1 by x minus n equal to 0, right? Because I have simplified the same expression and I've obtained this at the end. So what I'll do, I'll take that as my function f. So I'll consider f of x to be equal to 1 by x minus capital N. Then what will be f dash of x? Derivative of 1 by x is minus 1 by x square, and derivative of capital N would be 0. So that's f dash of x, right? And now how xn plus 1 is given by Newton-Raphson method. Xn plus 1 is nothing but xn minus f of xn upon f dash of xn, right? And this is f of xn will be 1 by xn minus capital N. So you just put x equal to xn in the expression for f of x, and f dash of xn will be minus 1 by xn square, right? So this will go on top as the reciprocal, and this will be nothing but xn minus, this minus will be plus, so this will be xn square, and inside the bracket I'll have 1 by xn minus n, right? So if I distribute this xn square, what I'll get? Xn plus xn square into 1 by xn is xn, and minus, I can just rewrite it down. So this would be xn. So xn square you open up inside, xn square by xn, one xn will disappear and I'll be left with xn minus xn square capital N, right? And if I take, this will be 2xn minus xn square capital N, and if you take xn common from there, you will end up with 2 minus xn into capital N, right? And that is the iterative formula that I'm talking about to find 1 by n. Okay, so n plus 1 approximate value will be given by xn, that is the previous one, into 2 minus capital N into xn. So if you want to find the reciprocal of any non-zero number capital N using Newton-Raphson method approximate value, then this is the iteration that you are going to use. All right. So let's look at a problem based on this now. Supposing I want to find 1 upon, I can frame the question as find the reciprocal of n is equal to 1.5349. Okay, that means I have to find 1 by n. Okay, that is to find 1 by n, and that will be nothing but 1 by 1.539. This is what I need to find, right? So I'm having sorry, I picked up a wrong n. That's 5349. Okay, I'll just change this to 49, and even here this is actually 49 and not 39. Okay, so that's my capital N that's given to me. Now I want to find 1 by 1.5349. The denominator, as you can see, is a bigger number compared to 1. So this number I'm expecting it to be less than 1, right? So approximate value of this I will assume that is x naught to be equal to 1. Okay, because this will be slightly less than 1, because I'm having a bigger denominator, so I can start with 1 as my initial approximation, right? So I will choose x naught to be equal to 1, and then using this iterative formula I can compute x1. So what will be x1? That will be xn, that is x naught into 2 minus nx naught, right? So I can put the data here. So 1 into 2 minus capital N is 1.5349 into x naught, that's 1, right? And you will see that x1 turns out to be 0.4651. Okay, 0.4651. You can verify this answer. And in a similar way now, I think it's pretty easy to compute the remaining approximations. You can see that x2 will turn out to be, or I can just write one step. So that will be x1 into 2 minus nx1 right, using the iterative formula. But x1 is already computed, that is 0.4651, so I will drop it here. 2 minus n is 1.5349 into x1, and x1 is 0.4651, right? So you can use your calculators to compute this, and this should be around, this will come to 0.5987, approximate answer this is 2348. Okay, you may have few more digits also, you can consider those if you wish to, otherwise you can leave it there. And now similarly you can compute the third approximation, that's x3, and this will turn out to be approximately 0.6471422071. Okay, so using the same iterative formula you can get this value of x3. You can verify whether this is correct or not. And x4, you will see that it is equal to 0.61, sorry, 0.65150, all right, 82403. So that will be x4. And x5 also I have computed few more approximations, so you can I'll just state them, you can verify the answer. x5, you will see that it comes to 0.65150,82403. Oh, I think I've already stated this. No, this was x5, and x4 was 0. Let me write. I made an error while writing x4. x4, you will see that it turns out to be 0.651478981. Okay, and x6 will be 0.6515082416. So that's very close to x5. And x7, I've computed till x7, and x7 you will see that it turns out to be 0.6515082416. So this would be the most, the correct closest value to 1 by capital N. Okay, so 1 by what was that number, 1.5349. You will see that this is equal to, after the 7th iteration, 0.65150082416. All right, so that's how you can use numerical, the Newton-Raphson method to find the reciprocal of any given number. All right, so I'll end the session here. Thank you.